the next two examples that we're going to look at, and the final two that we're going to look at in integration by parts, is going to be an example to where it doesn't matter sometimes how you select u and dv. You're going to turn it into this sort of iterated integral where no matter how many times you integrate it by parts, you're still going to turn out with something that doesn't reduce and to a non-evaluable sort of integral. And so we're going to have to solve it algebraically in terms of in the original integral. All right, now, be forewarned, these examples are a little bit long. And so let me show you the premise of why this is a rather difficult integral. Let's let u be equal to e to the 2x. Let's let dv be equal to cos 3x dx. Well, notice that if we take the derivative, chain rule, 2e to the 2x dx, and then reverse chain rule, or antiderivative, is going to be sine 3x over 3. Now notice that this did not reduce, right? So what if we flip them around? So in other words, let's let u be equal to the cosine of 3x. I mean, that's what we did before we had that one problem. So let's let u be equal to the cos of 3x. Well, we take the derivative of that, we get negative 3 sine 3x dx. Notice that no matter which way we decide, that the u will not simplify, all right? And we know that what happens when we take the derivatives of cosines and sines, they just iterate. Same thing with e to the 2x, it's just going to stay e to the 2x. So what happens when we get these integrals that don't necessarily reduce order of a polynomial, or we can't just say u is equal or dv is equal to dx? Well, here's the trick we're going to use with this. Let's define this to be I. Okay, I'm just going to call that the integral I. I'm going to let u, going back to our first definition, be e to the 2x. The derivative is 2e to the 2x dx. And then I'm going to let dv be equal to the cosine of 3x. And that means that v is going to be, or this should be dx as well. And then v is going to be sine 3x over 3. Now, this doesn't look promising because it doesn't look like it's going to reduce. But we're going to use our parts formula, okay? And we're going to say that I is equal to uv, which is going to be e to the 2x. Oh, this should be, by the way, not divided by x, but should be divided by 3. Apologies. So e to the 2x sine 3x over 3 minus the integral of v du. So that's going to be 2e to the 2x sine 3x divided by 3. And there's a dx in here, and there's a plus c. All right, so it doesn't look like we've made too much headway with this. I'm going to factor out a negative 2/3, or factor out 2/3 from this. All right, just so that way I can clean it up a little bit. So let's clean this up just a little bit. So that way it's a little bit nicer, although it's still not going to be nice. So here's our 2/3 on the outside, and we're going to have e to the 2x sine 3x dx plus c. All right, and this is a negative sign. Now, let's do integration by parts again. We're going to use the same definition for u. So u is going to be equal to e to the 2x. This time dv is going to be equal to sine 3x dx. All right. And I'll call that C1, although it doesn't matter. You can call it C. All right. Now, we're going to get the same derivative for du. So that's going to be 2e to the 2x dx by our chain rule. And then v this time, we're still going to divide by 3, but we're going to get a negative cosine since the antiderivative sign is cosine. So this is going to be negative cos 3x divided by 3. And it looks like that we're going in this infinitesimal circle as we're doing this, okay? But there is an end, okay? So we have uv v du. All right, so let's just do it and see what happens after this. All right, so we still have our I, which is our integral. We still have the e to the 2x sine 3x divided by 3. All right, so that's just this term being dropped down. I still have a negative 2/3. And I'm just going to go ahead and drop that negative 2/3 down. It's going to stay outside. And we're going to use our formula, uv v du. All right, so this is now going to be negative e to the 2x cos 3x divided by 3. And that should be a fraction bar. And then minus v du. So now be careful, lots of minus signs. So minus the integral of, we have 2/3 e to the 2x dx cos 3x. Okay, so that's going to turn into 2e to the 2x cos 3x divided by 3 dx. And we have a plus c2. All right, now this doesn't look good at this point. All right, because if you're noticing that unfinished integral, notice that unfortunately it still contains an e to the 2x cos 3x, and it's not going anywhere. All right, so something bad's happening with this. All right, and it looks like it's not going to be a value, but let's try to clean this up as best as we can. All right, and by the way, there should be another negative in here. All right, because we had uv, so the negative drops down here, and then v du, so negative 2/3 negative 2e to the 2x cos 3x dx plus c2. All right, let's try to clean this up a little bit, as much as we can. All right, so we have our integral I, we have our e to the 2x sine 3x divided by 3. We're going to end up with a positive 2e to the 2x cos 3x divided by 9. All right, so that's just this guy right here. We have a negative times a negative times a negative, and that's going to turn into a negative 4/9 integral e to the 2x cos 3x dx, and we still have plus c2. All right, so what are we going to do with this? All right, once again, we notice that we have to do integration by parts. And you're probably thinking, how many times can this go on? Well, it could go on infinitesimally if we were to use integration by parts, but we're actually 2 steps away from being done. Notice at the very beginning of the problem what I was equal to. I is equal to the integral of e to the 2x cos 3x dx. I want you to notice that that is precisely what this is. And so what I'm going to do is I'm going to replace that integral with I. So I get I, because remember that's the original integral, is equal to e to the 2x sine 3x divided by 3 plus 2e to the 2x cos 3x divided by 9 minus 4/9 I plus c2. Now we can isolate the I. So what I'm going to do is I'm going to add I to both sides, and I'm going to wind up with I plus 4/9 I. And when we add that together and get a common denominator, it's going to be 13/9 I. So I'm just going to write that as 13/9 I is going to be equal to e to the 2x sine 3x divided by 3 plus 2e to the 2x cos 3x divided by 9 plus c2. To solve, we're going to multiply both sides by the reciprocal or divide by 13/9. So let's just multiply both sides by 9/13. All right, so I, which is the original integral, is going to be equal to 9/13 times e to the 2x sine 3x divided by 3 plus 2e to the 2x cos 3x divided by 9 plus, I'm just going to call it c. And then finally, we can distribute, simplify. All right, so this is actually going to turn into I is mercifully 9 and 3 are going to simplify to 3e to the 2x sine 13, or 3x. I don't know where I got 13x from. Divided by 13. Right, we have a 9 and a 9. That's going to cancel out. So we have 2e to the 2x cos 3x divided by 13 plus our constant of integration c. All right, and we are finished. All right, so that's the trick with some of these integrals, where unfortunately, when we go to solve it, we have to make sure that we solve it in terms of the original integral. And we do have to keenly note what the original integral was and how that's going to factor into at what stage we can replace it with I. So notice right here, remember that we were able to replace it with I. Okay, so we do have one more example. We're going to go through, and fortunately, the next example is a little bit easier than this one, but it's still going to use the same technique.